So we're going to continue talking about congruences, congruence relation on the integers. Just a very quick reminder of the definition. If you've got integers a and b, another integer n, which we call the modulus, which is non-zero, then the definition of this relation, a congruent to b modulo n, that's how we say it, we read it, and this is defined in terms of divisibility. If n divides the remainder a minus b, or in other words, equivalently, if and only if there exists another integer q such that a minus b is equal to qn. Various ways of thinking it. Yet another way of thinking of it, as if and only if when you divide a and b by n will go in a certain number of times, and the small remainder that comes out, r, which is strictly less than n but greater than or equal to 0, the same remainder. So you notice I haven't put a subscript 1 and a subscript 2 on the r's, on the remainders. It's the same number here coming out. So n goes in a certain number of times into a certain number of times into b, but the remainder that you get, the small remainder that you get, the non-negative but strictly less than n remainder, that's the same for both of a and b. That's equivalent to saying a and b are congruent modulo n. Okay? This was our original definition. This is an alternative statement, which is the definition of the divisibility statement, and this was a theorem we proved, which was saying that having the same remainder is the same as being congruent. Okay. And then we have the system of integers modulo n, which is kind of the integers, except it's not an infinite set anymore. We put a subscript n to the bottom of it, and this is the set of congruence classes modulo n. So there are n congruence classes modulo n. Any integer is in one of these congruence classes. So this is the set of congruence classes. N. There are n of them, normally represented by, and there's various terminology used for these guys, but the standard residues or the standard representatives. Residues, residue of something that's left behind after something. So these are the residues after division by n. The small remainders you can't get rid of. Try as you might when you divide things by n, there's always these small remainders knocking around. Okay. These are normally taken to be the representatives that we talk about of these congruence classes, but they don't have to be. You can, in principle, you can choose any integer in any of these congruence classes to represent the congruence class. Okay. So it's the set of congruence classes, and remember, these form a partition of the integers. So if you got the set of all the integers, it can be subdivided into subsets, where this is the congruence class of 0, the congruence class of 1, congruence class of n minus 2, congruence class of n minus 1, and all the other congruence classes in between. Okay. So this is the picture that congruence classes partition Z. Okay, they split the infinite set Z into n different subsets. And the last thing we did, I believe, was from exercises 4.1, the first couple of parts of that, addition and multiplication can be extended, there exist natural addition and multiplication operations on Zn, where if you take two congruence classes, congruence class of A, congruence class of B in Zn, then the congruence class of A plus the congruence class of B was defined to be the congruence class of A plus B, and the congruence class of A multiplied by the congruence class of B was defined to be the congruence class of A times B. So we make those definitions. They look like good definitions of operations on the set of congruence classes. Give it two congruence classes. This is certainly another congruence class over here, A plus B, and the congruence class of A times B. It looks like two good definitions of operations. Of course, because each congruence class has an infinite number of elements in it, which could equally well have been chosen to represent them. So we could have chosen something else that was congruent to A, another integer. Of course, that would give you a different result in the square brackets. The things we proved in exercises 4.1, parts 1 and 2, is that these definitions do lead to well-defined operations on the set of congruence classes. Okay? So parts 1 and parts 2 show these definitions. That's a good way of saying it. They're independent of the representatives chosen. As you recognize, when you recognize that these definitions that we're defining an operation on the congruence classes, but to define it, we're choosing two representatives. So you have to worry about, well, what if you chose a different representative from this one, a different representative from this one? You would get a different integer in the square brackets, but what we proved in part 1 is that for the addition, you always got an integer in the same congruence class as A plus B. So in effect, it's defining the same object on the right-hand side. And similarly for multiplication in part 2. So that's a quick summary of kind of where we are up to now with congruences. Any questions about it, or any queries that you'd like to ask? Anything that was unclear? Or so in the rest of the chapter, what we're going to do is, in a moment, we'll look at the algebraic structure of these two systems, of Zn with the operation of addition and Zn with the operation of multiplication. Okay. These give rise to examples of groups, and we'll just put a little bit of terminology and basic results onto those. Okay. But beforehand, we're going to look at a quick theorem, Theorem 4.3. I'm going to leave you to read Theorem 4.3, so I don't want to disrupt my flow too much. I want to go straight on to look at these algebraic structures. So Theorem 4.3, just to introduce it to you, is a theorem about what you can do in these situations here, where you're looking at a congruence where you've got x times c congruent to y times c. Now, the simplifier in you wants to immediately get rid of the c. It's tempting, isn't it, to divide both sides by c. If this was an equation, you'd be perfectly justified to do that, as long as c was not 0, of course. But the question is, okay, this looks like an equation, but it's got 3 lines. It's incongruent. So are you allowed to cancel that C? Well, this theorem tells you how you can cancel a factor from both sides of the congruence. You can do it, but you need to potentially change the modulus. Okay, so the modulus needs to vary according to the greatest common divisor of this factor C with the modulus. Okay? So you need to divide the modulus by the greatest common divisor of C and M. And then as a special case, the nicest case is when that common factor C is co-prime to M. When it's co-prime to M, so that D is equal to 1, and so then the modulus won't change. You'll be able to just cancel the C from both sides, keep the original modulus, and then you have the simpler congruence that X is congruent to Y. Now the proof of that is a straightforward argument from the divisibility definition of congruence. Okay? But it kind of interrupts the flow here. It sits more naturally when we're looking at polynomial congruences, so I may come back and make reference to it. It's got a nice simple proof there just in terms of the definition of congruence in terms of divisibility. Okay, so moving on to modular arithmetic groups. So this is section 4.3. So you see, just above, the last thing I wrote down were both instances of this general kind of they're pairs like this. They're pairs of a set and an operation on the set. Okay, this is a very extremely common setup in mathematics, in algebra. We've got some well-defined set of objects and a nice operation on that set of objects. Okay? A way to, well, strictly speaking, it's called a binary operation. Binary, of course, means two things. And the two things are the two inputs, the A and the B, you add them together, or the A and the B, you multiply them together. So whenever you have a set and a binary operation on the set, then this is the natural setting of, or this setting is described mathematically by group theory. Okay? Now we gave you a quick introduction to group theory, or the notion of a group last year in Maths Fundamentals, but we'll just remind ourselves of it now. So this is the definition. So it speaks about a certain set G and asterisk. Okay, well, asterisk is a binary operation. Okay? So you can think of it as something like plus or something like multiplication, or in other contexts, probably the most important group operation is composition of functions, composition of transformations. Doing one thing after another, the effect of doing one thing after another. If you think about it, it's kind of a universal description of everything. Any topic or subject is really the study of doing one thing after another. Okay, but it isn't any old set and any old operation. We ask for certain basic patterns to hold, certain basic mathematical structure to be there, which when we look at it, we'll realize that it's common to a lot of operations that we've seen in our experience. And these are the kind of minimal set of properties that we ask for the pair of the set and the operation to make a kind of interesting mathematical structure. Okay? We don't want to ask for too much. If we ask for too many nice conditions, too many nice properties, then we're restricting the universe of what we're talking about. Okay? We're asking our objects to satisfy more and more properties. We're reducing the number of objects we're potentially looking at. Okay? But at the same time, we want to ask for enough properties so that we're restricting the field a little bit, so that the things we're looking at have some commonality and have some nice structure that we can describe. Okay, so there's 4 properties that this pair, the set and the operation on the set, have to satisfy. First one is closure. So whenever you take a pair of elements in the set and operate them together with the operation A star B, so you think of A star B, something like A plus B or A multiplied by B. These 2 examples we're going to focus on. So the first thing is the set must be closed. So the product of the two elements under the operation must also be the set. And the second property is associativity. Associativity refers to when you're forming a triple product, A star B star C. Now star is only a binary operation. Okay? All star knows how to do is take the input to its left, the input to its right, combine them together and produce the new element. So a triple product is a little bit ambiguous. It either means this, A star, the result of B star C, or it means the thing on the right, A star B, the result of A star B star C. Okay? And associativity is when these two are always the same. Okay? So when it doesn't make a difference how you parcel up the triple product to evaluate it using the operation. Note that the order of the A and B and C are not changing, just the way we're pairing them together to evaluate it in a 2x2 fashion. Third property is the existence of an identity. So there's a very special element in the set which has this property. Now when you take the product of it with A on either side, it gives you back A again, and that this holds for every A in the set. Okay? Fourth property is existence of inverses. So an inverse of an element A is this element. We normally write it A superscript minus 1. A superscript minus 1, when you take the product of it with A under star, it gives you the identity. And so does the product in the opposite order as well. Okay? So those are identity elements. And the fourth property, the identity axiom, says every element in the set has an identity in the set. So for every A in G, there exists an A inverse in G, and the A inverse is the inverse of A. Could be that A sometimes equals A inverse. We're not saying that the A inverse is necessarily a different element. Okay, A could be its own inverse. It could be that A squared is equal to the identity. But these are the small set of properties that we attach to this term. Okay, so a group is any set, an operation that satisfies these four properties. Okay? So these are enough properties to place an interesting mathematical structure on the set, but they're not too many properties so that we're cutting out too many things from our discussion. Okay? So those are in the notes in definition 4.6. So theorem 4.5 says straight away that the system Zn with addition is a group. Okay, this is a finite. Of course, it's finite. This is only a finite number of congruence classes, but this is a group. So to prove it's a group, we just have to show that the four properties hold. Okay. So we show the four properties hold. Now we won't ask ourselves to do too much technical foundational work here. If some of these proofs will just be kind of, observing that the property is known to hold, or that the property we're talking about is a well-known property that we use all the time and is a common part of our discourse. So the first thing is closure. Is the operation closed? If I take two congruence classes, is the congruence class of A plus B another congruence class modulo n? Yeah, it's true by definition, okay? We defined the sum of congruence class of A and B to be the congruence class of A plus B, okay? This is clearly, so the operation is clearly closed, okay? It just follows from the way we've defined it, okay? associativity. I have to think carefully about this. A plus B plus C. Okay, take it for granted that these are three congruence classes from Zn. Well, by definition, this is congruence class of A plus the congruence class of B plus C. Fair enough. By definition, this is A plus the B plus C, and it's the congruence class of that. Okay. Now, what can we say about, of course, remember the results we're aiming for is to get congruence class of A plus congruence class of B plus congruence class of C. That's what we're aiming for. So what step can we make here? Remembering, of course, that our pluses, some pluses are different than other pluses. These pluses here is the new operation that we're talking about, the addition of congruence classes. Okay? The pluses you see inside the square brackets, that's your primary school addition of integers. Yeah? That's the pre-existing operation of addition of integers. Okay, we use the same symbol for them because they're intimately connected, these two operations. But strictly speaking, they're different operations because they act on different objects. Yeah? They're operations on different sets. So there's a very compelling thing to use here, is to use the associativity of addition on the integers. Okay? We're well used to the idea that adding a bunch of integers, it doesn't really matter how you add them up. Okay? The sum is always the same. So this is by associativity of addition on the integers themselves. Okay? So we're using a pre-existing property, associativity of addition on the integers. And of course, then when you're looking at this is the congruence class of a sum of two integers, A plus B and C. So by definition, that's the congruence class of A plus B plus the congruence class of C. So the justification for every other step is the definition of addition of congruence classes. Yeah? So all other steps justified by definition of plus on Zn. Okay. We define addition of congruence classes as congruence class of the sum of the integers, the sum of the representatives. This is clearly associative now, isn't it? A plus B plus C is the same as A plus B plus C. Okay. And very commonly, we see this kind of theme coming out that the new operation we've defined, it was defined using this pre-existing operation, addition of integers, and the property of the new operation, the associativity of the new operation, comes from the associated property of the ingredient operation, or the ingredient. So the properties of the ingredients give you the properties of the new thing. Again, that sounds like a very universal property. Property, or the way that the new thing behaves, comes from ultimately the properties and the way the ingredients behave. Identity. Is there one? What's the identity? So what we're looking for is some congruence class that when you add it to another congruence class, it gives you back the same congruence class. Well, it's a congruence class of something, and whatever goes in there, we end up adding it to the A. So the easy way to make sure this congruence class remains as the congruence class of A is to choose the congruence class of 0. Okay. So clearly, the congruence class of 0 is the identity. And inverses, if you have a congruence class of A you're looking to add it to something, and you're looking to get back the identity element. So it's got to be a congruence class. I've got to have a pair of square brackets. I just have to decide which congruence class. So which representative, when you've added it to A, place you in the congruence class of 0. Well, there's many different choices, but the simplest choice would be just the negative of A. If you add A and minus A, you of course get 0. Okay. So the additive inverse of A is its, and we may as well call it the negative, the congruence class of minus A. So it's a group. It satisfies the 4 properties. So that immediate, and an awful lot of theory and properties are known about groups, and it gives you a nice algebra, a nice mathematical structure, a nice way to talk about the properties of the system. Now, groups, or at least small groups, are often visualized. Look at a group on the page, on the computer screen, by their Cayley tables. So Cayley tables, named after Cayley, are their operation tables. And I think we looked at some of these last year. It's fundamentals. The operation table for a system. So in general, if you had your group with the operation star, what you do is you list the elements of the group along the top as column headings. You list them down the bottom as row headings. And in the body of the table, in the row corresponding to GI and the column corresponding to GJ, you put the product GI star GJ. So it's a way of displaying in a nice table all of the possible products that lie within the group. Okay. So, e.g., let's have a look at the Cayley table for Z4. So there's 4 congruence classes. Now, if you look at this previous page, and this previous page, we had square brackets all over the place. And, mathematicians like to be efficient, quick. I like using these expensive pens, and I don't like wasting the ink on them too much. So, you see, I've already started, did these square brackets all over the place really serve a purpose? Well, of course they did. They're there to remind us that we're not talking about integers now. We're talking about congruence classes of integers. But as long as we understood that, as long as we're all on the same page and we know that really we're talking about congruence classes of integers, the presence of all these square brackets all over the place, isn't really playing a role after that, right? If we understand that what we're talking about is operations on congruence classes, then you see we'll dispense with the square brackets, because we understand what we're talking about. Okay? Although, you do have to be careful, because, most of the time, the operations of addition and multiplication on these congruence classes, you make use of the already known properties of normal addition and normal multiplication of integers, but sometimes there's differences. So this is addition. So we want to add 0 to all these. So when you add 0 to any of those, of course, it doesn't change it. When you add 1 to these, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and you don't write down 4, okay? Because 1 plus 3 is not 4, it's 0. Okay, because we're talking about addition of the congruence classes. Okay, it's not, strictly speaking, incorrect to say a 4 here, but we recognize that the congruence class of 4 is the same as the congruence class of 0 modulo 4. And we've got a set of symbols already for the 4 congruence classes. We don't want to keep renaming them under other names. We'll use these names all the time. Okay, so you got 2, 3, 0, 1, 3, 0, 1, 2. Okay. Now, it didn't take me long to write down that Cayley table, and the Cayley tables for Zn plus actually all follow this pattern. There's no great mystery to what the Cayley table of addition on the integers modulo n is. The top row of course, because you're adding 0 to everything, we'll just leave everything unchanged. And then when you add 1 to everything, the effect of that is to slide everything one place to the left from the row above. Except the 0 doesn't slide off the edge of the table, it wraps around at the back and comes in. Okay. And that pattern repeats all the way down. Okay, just like we did here. Each new row is just the previous row cyclically cycled one place to the left. Okay, so really, in group terms, the system of integers modulo n under addition isn't really all that complicated. There's the congruence class of 0, the congruence class of 1, the congruence class of 1 plus 1, congruence class of 1 plus 1 plus 1. Everything can be represented as 1s added together. So this is the cyclic group generated by at least this element. It will be generated by other elements as well. So every congruence class, modulo n, can be constructed by adding together the appropriate number of copies of the congruence class of 1. And that feature, that everything in the group can be generated using a single element and the group operation, that feature means the group structure is extremely simple in the grand scheme of things, and it's well understood. Things get interesting when we start to look at the multiplicative modular arithmetic. But that's the additive one. Any questions or queries about it? Okay, so let's move on to multiplication. Can we immediately launch into the same theorem that we just proved about addition on the integers mod n? Can we just prove the same thing for multiplication of Zn? Well, nearly. Closure is fine. Okay, the congruence class of A times B will always be in Zn if the congruence class of A and B are. Congruence class of A and congruence class of B. Associativity is fine. Exact same proof. Proof we had for associativity of addition, just change every plus to a multiplication sign. It's exactly the same argument, okay, for multiplication. Just multiplication, 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 okay. So associativity is fine, same proof as for plus. Identity is there. It is what? The congruence class of 1. That's the congruence class that when you multiply it by any other one, it doesn't change the other one. Because you just multiply the representative by 1. Congruence class of A multiplied by congruence class of 1 is congruence class of A times 1, which of course is congruence class of A. Inverses are fine, of course. Inverses are around. Or are they? Question mark. Right. Of course, there's inverses. The inverse of A is the congruence class of 1 over A. Obviously, it's easy. Except, what is 1 over A? Well, if you multiply it by A, yeah, you do get 1, but 1 over A is not available. We're talking about the integers, aren't we? 1 over A is not in our present discourse. Okay, it's a fractional quantity. Unless A is plus or minus 1, in which case it's the reciprocal is an integer. Okay? But really reciprocals aren't integers. So that's no good. Okay? That's not what we're talking about. Okay? So try again slowly. What are we asking for when we're asking for inverses? We're asking for, suppose a congruence class of B was the inverse of A, or is the inverse of A. What this means is that the congruence class of A times the congruence class of B is the congruence class of 1. Well, what does that mean? That means the congruence class of A times B is the congruence class of 1. Now that doesn't mean A times B is 1. It means its congruence class is the same as the congruence class of 1. So that's true if and only if A times B is congruent to 1 modulo n, whatever the modulus is. It doesn't mean B is equal to 1 over A. This was an equation amongst real numbers. Yeah, B is equal to 1 over A when I say A is 0. But we're talking about congruences amongst integers. What does that mean? This means n divides the difference between these two quantities, AB minus 1. That means, so I'm just rolling with the definitions. That means there exists an integer q such that AB minus 1 is q times n. Or in other words, there exists a q in Z, and there exists a b as well, such that 1 is a times b minus qn. Now, what's that? That's a linear combination of the a and the n that's equal to 1. The a and the n are the two objects of interest at the beginning. We're investigating when a might have an inverse. It has an inverse when there is a b such that we can form this linear combination for some q that gives us back 1. Okay? But by result from the previous chapter, this is true if and only if the GCD of a and n is 1. Okay? So there are inverses around. There are inverses around, but only for those representatives or those congruence classes, which are congruence classes of integers co-prime to the modulus. Okay? So the only congruence classes A having inverses, multiplicative inverses modulo n are those where the GCD of A and n is 1. Yeah, so the only congruence classes, congruence class of A, that have multiplicative inverses mod n are those where the greatest common divisor of A with the modulus is equal to 1. So we can form a group, but we have to reduce our set, potentially. So to form a group, and we indicate this by putting a superscript of the multiplication sign, or some authors use an asterisk, but something that indicates the multiplication going on. And this is the set of congruence classes A from Zn, but GCD of A and n is 1. Okay? So it's the congruence classes that are co-prime to the modulus. Then everything checks out. The operation is still closed, although, well, let's prove this actually. Yeah. So now we can form this theorem that Zn, this forms a group. So this theorem 4.7. Closure. Well, you see, already we've got to prove a little bit about closure. Because if we take two congruence classes, A and B, that are in Zn, the product of them is the congruence class of the product. Is this in Zn star? Well, it may or may not be. Okay. We need to know that the GCD of A times B with n is 1. But this is a previous exercise about greatest common divisors. Page 16. Question 10, part C, proves this. This shows that if the GCD of A and n is 1, then the GCD of B with n is equal to the GCD of AB with n. And because the GCD of B with n is already 1, because B is something from here, we'll note that this is equal to 1. It's equal to 1 since the congruence class of B is in the reduced set. So it is closed. If you take two things that are congruence classes of integers co-prime to n, multiply them together, you again get a congruence class that is co-prime to n. Associativity is still true. Associativity was a property that about how the operation worked on any possible inputs to it. And we've just slightly reduced the set of inputs, so that's not going to change that property. Associativity still holds true. The identity axiom is still there. Identity is fine as the GCD of 1 and n is equal to 1, so the congruence class of 1 is present in the reduced set. So we do have an identity element. And inverses are fine also if A is in Zn prime, then the GCD of A and N is 1, and that implies that there exists a B such that the congruence class of A times the congruence class of B, okay, as above. Okay, we argued for that when we were doing this development here on the previous page. If the GCD of A and N is 1, that's the same as saying that there is an inverse B for A. Okay. And this new B, which is equal to the inverse of A, this will be an element of Zn, the reduced residue system. Okay. So this is a group now. Sometimes called it's called the multiplicative modular group. And the way we've chucked out everything which is not co-prime to N, and this means it's the reduced residue system. Well, that's just a term we can use for it. Okay, so in the tutorials we'll do a little bit more investigation of these. In particular, just something to walk away from the lecture today with. Now, when I put down P, it's understood that P is prime. If P is a prime, well, if we're forming the multiplicative group, we have to throw away everything which is not co-prime to P. So everything which has a non-trivial greatest common divisor with P from the residues between 0 and P minus 1. But of course, P is a prime number. So it doesn't have any common divisors to share with anything apart from 1 and itself. Okay? So 0 is divisible by P. So the greatest common divisor of 0 and P is going to be P. So that's the one we throw away. But all the other ones, because P is a prime number, all the other ones are still here. Okay? Because everything less than P, everything non-zero less than P is co-prime to P. So we only chuck away, only discard the congruence class of 0. Okay, so when P is prime, these things have a so P minus 1 of these. When P is prime, these are special interesting cases. Okay, so we'll investigate these things further with some exercises and problems and examples in the tutorials this week. If you look at the remaining examples that we haven't worked through and the exercises, those are the things we'll be looking at in the tutorials this week. Okay.